All right, y'all. In this video, we are going to do the last section in chapter 5. This is called the substitution rule, which is also can be shortened. You'll hear me say a lot today called U substitution. This is one of the, outside of just doing basic antiderivatives, this is probably one of the stronger rules that we will do and more popular rules. So we're going to do a lot of U sub throughout this class. So we're going to make sure throughout this video that you understand how to go about this process. So let's talk about for a second, when is the substitution or U substitution rule needed? So if we can define U as being a function that is differentiable on an interval and continuous, we can say that the following is true. If you are trying to integrate a composition function, so remember compositions are stuff like f of g of x. If you need to integrate a composition function where the derivative of it is outside, then you can rewrite this as the integral of just f of u du and use your regular antiderivative rules that we've covered the last few sections. Now, if you look at f of g of x, g prime of x, that looks very similar to the formula for chain rule that you did in Calculus 1. And it's what it is. You're trying to undo a chain rule. The way to undo a chain rule is to do U substitution. So to kind of show you what I mean, I decided to put an example right below the instructions. So essentially, in more layman's terms, the idea here is to replace a relatively complicated integral by a much simpler integral. So if you had something like the integral of x squared times the square root of x cubed plus 1, how could we go about integrating this? Well, the hint here is that whatever is inside of a function, so like this x cubed plus 1, that is what you're trying to change. So if we were to let u be x cubed plus 1, then we could also take the derivative of this, because the next problem is going to be you can't leave a dx here. If you change this to u, you have to make everything u's. So if you remember back in Cal 1 when you did differentials, this is the idea of differentials. You would say that the derivative of u is du. The derivative of x cubed would be 3x squared dx. And then you can use your idea of these just being differential and linear operators to get the dx by itself. So if I were to divide the 3x squared over, I could say that dx is equal to du over 3x squared. Now you go back to your original integral, and this is where the substitution happens. This can be rewritten as the indefinite integral of x squared times the square root of u times my dx term, which is du over 3x squared. And what should happen majority of the time is that when you plug your linear operators in, you notice that all of your x's will usually cancel. Now, if they don't, that's usually an issue that we'll talk about in a little bit. But for now, everything should cancel. This extra 3 on the bottom, which is an understood 1/3, can be factored out in front of the integral. And then remember, you can't integrate a square root function as it sits, so I'm going to go ahead and rewrite that as u to the 1/2 du. Now your substitution's done. You now can do your antiderivative to finish this off. So this would be 1/3 times, if you add 1 to the power, that would be u to the 3/2. And instead of dividing by 3/2, I'm going to multiply by its reciprocal, which is 2/3. And since this is indefinite, please don't forget from the last video that this needs a plus c. Putting together the 1/3 and the 2/3 together will give us a 2/9. And here is the big kicker. Since the original integral is in terms of x's, your final answer must also be in terms of x's. So this u here, you need to substitute your u function back in, which earlier we called that x cubed plus 1. You will raise that to the 3/2 power and then plus c. And this is the idea of U substitution, or just the substitution rule. You're trying to take a really complicated function, which we did, the integral, and you made it into something very simple. And then after you finish integrating, you resubstitute your values back in. And like I said, this rule is very, very, very popular. We will use it pretty much the entire semester throughout different concepts. So make sure we get this under control as we learn it. So let's go through and do some more examples. So the rest of the problems for the next little bit are just going to be substitution problems. So what if you want to do the indefinite integral of x cubed times e to the negative x to the fourth? So the issue with this one is that based on your antiderivative rules, we don't know how to integrate e's that have these ugly powers to them. That has to be something simple like an x or a u in our case. So when I do my u substitution here, I'm going to let u be the power of e. So in order to convert everything into u's, I need to do my idea of differentials. So the derivative of negative x to the fourth is negative 4x cubed dx. And then if I solve for dx there, so I can plug it back in just a second, I can say that du over negative 4x cubed is equal to dx. So plug in your information into this integral. So we will have the indefinite integral of x cubed times e to the u multiplied by your dx term, which is du over negative 4x cubed. And like I said on the last problem, the first thing you know you're on the right path is what if your x cubes cancel. So those are completely gone. This negative 4 on the bottom can be factored out front as a constant as negative 1/4 times the integral of e to the u du. That's one of your antiderivative rules you should know. The antiderivative of e to the u is just e to the u. It's indefinite, so we're going to put a plus c on the end. And then to wrap up your problem, you need to substitute your u back into your answer before you type it in your homework. So this is negative 1/4 e to the negative x to the fourth plus an arbitrary constant c. And that is your final answer for number 2. Once again, whatever the inside function is, so since the negative x to the fourth was inside the e function, that's why we let it be our u. All right, so let's do one that has to do with trig functions. So what if you're asked to do the indefinite integral of cosine cubed theta times sine theta d theta? So while both of these are trig functions, when you're trying to decide what your u should be for u substitution, you want to do the one that's inside of something. And since this cosine function is being cubed, I'm going to let u be cosine of theta. And then I'm going to use my differentials idea to solve for everything else. So du would be negative sine theta d theta. And then getting d theta by itself, I can divide both sides by negative sine theta to say that du over negative sine theta is equal to d theta. Substituting all this information in, you should be able to write this as the indefinite integral of, that becomes u cubed times sine theta times du over negative sine theta. Very nicely, the sine thetas do cancel. That extra negative on the bottom can be factored out in front of your integral. So this is the negative integral of u cubed du. And that right there is just an anti-power rule. So you can add 1 to the power and divide by the power. So this is negative u to the fourth over 4 plus c. And then you resubstitute your u value back in. So this would be negative cosine to the fourth of theta over 4 plus an arbitrary constant c. And that is another example where u sub can be used to help you with trig. All right, like I said, just kind of continuing on here. Let's do the following. What is the indefinite integral of x squared times 4 minus x cubed all raised to the 2/3 power? So remember, when you're doing these u substitution problems, you want to pick the function that's inside of another function as your u. So in this case, I'm going to pick this inside function here. So I'm going to let u equal 4 minus x cubed, and therefore du is going to equal negative 3x squared dx, and then du over negative 3x squared is equal to dx, as far as my differentials and linear operators go. Substituting all this information in will give us the indefinite integral of x squared times u to the 2/3 times my dx term, which is du over negative 3x squared. And you're starting to notice a pattern here of when things will start canceling. In this case, the x squareds cancel. That negative 3 on the bottom, when you factor it out in front of your integral, becomes a negative 1/3, and you're going to integrate u to the 2/3 with respect to u. So this is another example of adding 1 to the power and dividing by the power. So if you add 1 to 2/3, that would give you 5/3. But instead of dividing by 5/3, I'm going to multiply by its reciprocal, which is 3/5. All right, and then you're going to have an arbitrary constant c because it is an indefinite integral. All right, when you put the two constants together in the front, actually very nice here, the 3's actually cancel to give us a negative 1/5. We're going to replace our u with the original u substitution, which is 4 minus x cubed. We're going to raise that to the 5/3 power, and then don't forget your plus c. And that is your answer to number 4. Hopefully by now, and we still have some more problems to do, but by now, hopefully you're starting to notice the pattern. The inside function becomes your u. You set up your u substitution, and hopefully everything other than the constant variable u's cancel, and you're able to integrate. All right, let's do a couple more like this, and then we'll go on to a couple that are a little bit different. So what about the indefinite integral of the natural log of x all squared divided by x dx? All right, so in this case, it's pretty easy to see that the only function that's inside of another is this natural log function. So when I go to set up my u substitution, I'm going to let u equal the natural log of x. When you take the derivative of that, it becomes 1 over x dx. And a little bit different this time, it's not division. To get the dx by itself, you would actually multiply both sides by x. So you could say that x du is equal to dx. So a little different there. After you do all that, you're still going to substitute everything in. So this would be the indefinite integral of u squared over x times my dx term, which is x du. Still the same thing happens. It's a little backwards this time, but x over x does cancel. And this will give us the indefinite integral of u squared du. Add 1 to the power and divide by the power. So this is u cubed over 3 plus c. And then replacing your u back in will make this the natural log of x all cubed divided by 3 plus an arbitrary constant c. So hopefully you're starting to tell that it doesn't have to be a polynomial function to let your u. The u's can be polynomials. We've seen trig. We're now seeing natural logs. It all depends on, as long as you have enough information, the u can be anything as long as it works out when you go through the process. So very good. So let's do one more straightforward one, and then we're going to do one that maybe is a little bit trickier. So example number 6. What is the indefinite integral of the arctangent of x all squared divided by x squared plus 1 dx? Just like the natural log problem we just did, it's pretty clear to see what your inside function is going to be here. So I'm going to let u equal the arctangent of x. And from Cal 1, hopefully you remember that the derivative of arctangent is 1 over x squared plus 1 dx. And then to get the dx by itself, I'm going to multiply both sides by the x squared plus 1. So I could say x squared plus 1 du is equivalent to dx. When I substitute all of this in, this will be the indefinite integral of u squared over x squared plus 1. And then my dx term is going to be x squared plus 1 du. Very nicely, the x squared plus 1's cancel here, and you're left with the indefinite integral of u squared du, which, just a coincidence, is the same thing we just had. You would integrate it the same way to get u cubed over 3 plus c. And then when you resubstitute your u back in, you're going to end up with the arctangent of x, all cubed, divided by 3 plus c. And that is your answer to number 6. And for the most part, that is how 90% of the u substitutions will work. You'll find out what your u is, solve for dx and du, and then substitute everything in to make it a very easy integral. But the next problem we're about to look at is what happens. You notice that everything is canceled perfectly every time. What if it requires you to go an extra step further? So for example, number 7, how would we do a problem like this? And it looks very similar, but we're going to run into an issue in the process. So what is the indefinite integral of x times 2x plus 5 all raised to the 8th with respect to x? Now, on its surface, it looks the same. The inside function is pretty clear here, and that's not any different. That is going to be your u for your u substitution. So if I let u equal 2x plus 5, then I can say that du is 2 dx. And then getting the dx by itself would say that du over 2 is my value of dx. But when you go to plug all of this in, you're going to see an issue that arises. This would be x times u to the 8th times my dx term, which is du over 2. That extra x did not cancel. The only thing you can do at this point now is that extra 2, which is a constant, you can bring it out in front of your integral, and we have 1/2 times the integral of x times u to the 8th du. This can't be integrated yet. You're going to have to find another way to get rid of that x. That is where your original u substitution comes in. This will be your first example of what we call a double substitution. If you look in this problem at the very beginning, over here on your u, there's an x right there that if you could get by itself, you could put this in terms of u. So from this first original u sub, if I were to solve for this x by subtracting 5 and dividing by 2, you could say that u minus 5 over 2 is equal to x. So why don't I let this x be this form of u? It's just a secondary substitution we have to make. So this would be 1/2 times the indefinite integral of u minus 5 over 2 times u to the 8th du. All right, we pick up an extra constant. This 2 on the bottom doesn't have to stay here. You can factor that out to the front to make this a 1/4 times the integral of u minus 5 times u to the 8th du. Still can't integrate this yet, so we're going to go one step further. We're going to distribute that u to the 8th to both terms to make this a 1/4 times the indefinite integral of u to the 9th minus 5u to the 8th du. And after a little bit more work than the last 6 problems we've done, you can now integrate this function. So this would end up being 1/4 times, this is u to the 10th over 10 minus 5 u to the 9th over 9 plus c. Substitute your original u back in, and you will get 1/4 times 2x plus 5 to the 10th divided by 10 minus 5 times 2x plus 5 to the 9th over 9 plus c. And then if we distribute that 1/4 to both of these fractions, you can write your final answer as 2x plus 5 to the 10th over 40 minus 5 times 2x plus 5 to the 9th over 36 plus c. And that's an example where you have to do what I like to call a double substitution. The original u sub was correct, but you picked up this extra x that you had to solve for in your u sub in order to substitute that in as well. So that's one of the longer ones you may have to do in this section when it comes to u sub. But good job. The last thing we need to go over now is, as you probably have noticed, is that every single u substitution we've done so far has been an indefinite integral. And maybe you were thinking, well, can you do definites? Oh, you can, but you're going to have to do an extra step or two to get it to work. So the definition for a substitution rule of definite integrals is exactly the same. Your ultimate goal is still to change this ugly chain rule into something very simple. That part will be absolutely no different. The difference is that your A and your B have to get changed to G of A and G of B. That means whatever you let your U substitution be, you will have to plug your original parameters into that function to get your new parameters. You cannot use the original parameters to integrate a U substitution. That's because A and B, you see, are in terms of x's. You need to get everything in terms of u's. So let me kind of walk through what you have to do. So if you have the definite integral from 0 to 1 of the cosine of pi x over 2 dx, well, when you're doing your u substitution, you're looking for your inside function. So in this case, I'm going to let u be pi x over 2 du. The derivative of pi x over 2 is just pi over 2 dx. And then to get the dx by itself, I'm going to multiply both sides by 2 over pi. So 2 over pi du will equal dx. The extra step here, I'm going to do all my work over here on the right. You cannot integrate from 0 to 1. You will need to take the 0 and the 1 and plug them in for x in your u substitution to get your new parameters. So for example, if you let x be 0 right there, pi times 0 over 2 is going to be 0. So your lower parameter actually didn't change, just coincidence there. But when you plug 1 in, pi times 1 over 2 changes your upper parameter to pi over 2. And then you do the rest of your u sub the same. This would be the cosine of u times your dx term, which is 2 over pi du. The 2 over pi is just a constant, so you can factor that out front. That's all I'm going to do on the next step. Cosine of u is one of your antiderivatives you should know. So this would be 2 over pi times the antiderivative of cosine is sine of u, but now you have to evaluate this from 0 to pi over 2. So this would be 2 over pi times sine of pi over 2 minus the sine of 0. Evaluate both of those. So the sine of pi over 2 is 1. The sine of 0 is 0. And 2 over pi times 1 minus 0 would just be 2 over pi. And that is the idea you have to do definite integrals of u substitution. You must change your parameters. And I'm going to harp on that a lot because that's the number one mistake in my 9 years of being at MSU. Students don't change parameters even after me stressing it for 9 years here. So let's do a couple of more just so I can kind of keep hammering this idea for you. So what if we do the definite integral from 1 to 2 of e to the 1 over x divided by x squared? All right. Similar to the e problem we did a while back, the inside function here is this 1 over x, because you don't want e raised to a funny power. So what we're going to do is we're going to let u be 1 over x, which keep in mind is the same thing as x to the negative 1, because you'll have to do the derivative of this to get your du. So taking the derivative, I would say du is negative x to the negative 2 dx. And then if you get your dx by itself, this would be du over negative x to the negative 2 is dx. Now, when I come over here to rewrite my integral, you need to take your original parameters and plug them into your function of u to get your new parameters. So if you plug 1 in, 1 divided by 1 is 1. Plugging in 2, 1 divided by 2 is a half. This will become e to the u over x squared times my dx term, which is du over a negative x to the negative 2. The negative in front of this x actually just comes out front, and you're going to integrate from 1 to 1/2. X squared and x to the negative second actually cancel each other, and this just leaves you with an e to the u du. Now, one thing you will notice here is that your parameters are backwards. 1 to 1/2 is not correct. You must go from your lower parameter to your upper parameter. So remember your property. You can flip over your integration limits as long as you bring a negative out front. But since there's already a negative out front, when you flip your parameters around, it just becomes the positive integral from 1/2 to 1 of e to the u du. Integrating e to the u is pretty simple. It's just e to the u, and we're going to evaluate this from 1/2 to 1. This will give me e to the first minus e to the 1/2, which is the same thing as e minus root e. And that is your final answer for this definite integral. All right, let's do one more. This is probably the most clever one because you're going to have to rewrite something to make the u sub work. So what if you want to do the definite integral of e to the x over 1 plus e to the 2x dx? The difference in this one is that the temptation here is to let e to the 2, or let 2x be your u substitution. Unfortunately, that's not going to really help you here. The difference in this one is that you're probably going to have to rewrite the problem a little bit. Usually the goal is when you've got multiple exponential functions, you want them all to be the same as a core. I'll call it that. So when I go to rewrite this, I have no problems with the e to the x on top. The problem is that I need this e to the 2x to also be an e to the x. And the only way to get it that way is I need to rewrite this as e to the x all squared. And by doing that, dx. And by doing that, what I've now done is I've created a new inside function, which is now e to the x, that I can use as my u substitution. So if I let u be e to the x, then du is going to be e to the x dx, and therefore du over e to the x is dx. You still must change your parameters. So I'm going to take the 0 and the 1, and I'm going to plug them in for my x in my u substitution to get my new parameters. So by doing that, you will get the integral. E to the 0 is 1, and e to the first is just e. So you're going to integrate from 1 to e of e to the x over 1 plus u squared times my dx term, which is du over e to the x. And now you can see, here's another good reason why it was good to rewrite this, because now these e to the x's cancel, and you're left with the integral from 1 to e of 1 over 1 plus u squared du. And that is one of your antiderivative rules you should know. This is actually the inverse tangent of u, and we're going to evaluate this from 1 to e. So that would give me the inverse tangent of e minus the inverse tangent of 1, and you only have to evaluate it if it's possible. We don't know exactly where tangent's e at, so I'm not expecting you to know that, so we can leave that as inverse tangent of e. But we should all know what angle makes tangent equal 1, so therefore the inverse tangent of 1 is pi over 4. And while that looks very unorthodox, that is actually the correct answer for this. Your answer would be the inverse tangent of e minus pi over 4. So that's probably the biggest critical thinking. But once again, when you've got multiple exponential functions, the first rule of thumb is to get them of the same kind, because otherwise no kind of substitution is going to make a difference. Trying to do a u sub with two different e's is going to cause for a big issue going forward. Now, at the very end of this section, there's a couple of, one really small thing I want to end on to wrap up chapter 5. And that's because in the chapter 6 we're about to get into, we're going to deal with a lot of symmetry. And I want to introduce what symmetric functions actually involve when it comes to integration. So what integrals of symmetric functions says is that suppose that you have a function that's continuous on the interval negative a to a. If f is an even function, which means that f of negative x equals f of positive x, then you can rewrite your integral from negative a to a as 2 times the integral from 0 to a. So essentially, instead of having to do a negative lower parameter, you can change your lower parameter to 0 and just double that integral. It'll be a lot easier to work. Even better is that if f is an odd function, all you have to do is say that the integral from negative a to a is going to be 0, because both sides would end up canceling each other out. So let me show you a couple. We're not going to work these all the way out. We're just going to kind of show you how they set up, because we'll use some of this in the next chapter. So you have the integral from negative pi over 3 to pi over 3 of x to the 4th cosine x. And your job first is to figure out, is this an even or an odd function? So if I were to call this f of x, the only way to check whether it's even or odd is to evaluate f of negative x. So I'm going to take both of those x's and I'm going to make them negatives. Well, negative x to the 4th is just going to be x to the 4th. And what you should remember from trig is that cosine is already an even function, which means the negative will just go away. So by plugging negative x into the original function, you got the exact same thing. This is the definition of an even function. And that being said, this means what we could do going forward is you could rewrite this integral as 2 times the integral from 0 to pi over 3 of x to the 4th cosine of x dx. Like I said, we're not going to integrate this right now. We haven't even learned how to integrate this yet. So, but that's kind of the idea. If it's an even function, you are able to double the integral and it makes the parameters a little nicer. All right, and then you probably can guess the next one's odd, but let me show you why. So if we integrate from negative pi over 3 to pi over 3 of x squared sine of x, if I were to define this as my function f of x, and I test what kind of function it is, this would be a negative x all squared times the sine of negative x. Well, negative x all squared is just x squared. And since sine is already an odd function, this negative would just come out front, and you could rewrite this as the negative x squared sine of x. These are opposites of each other. If the only thing that changes when you plug negative x in is that you get a negative out front, this is the definition of an odd function. So in the end, this is an integral that you can actually solve without doing any work. The integral, as long as the two values are the same, and one's negative, one's positive, and it's an odd function, your answer is automatically 0. That is an idea that we're going to use a lot because the first few sections of chapter 6 are all about doing applications of graphs. So we're going to look at some of that even and odd stuff and symmetry. But congrats, that ends chapter 5. That's the first full chapter of this class that you've covered. In the next video, we will start chapter 6. We're going to talk about how do you find the area if you've got multiple curves on the same graph and you need to find the area between them. And that will be the beginning of chapter 6. See y'all then.